We'll start off slow. We'll pick up steam as we go. Gases generally have what? Well, let's see. We have 5 possibilities. Low density is a good one, yeah. Maybe I'll better move it, expand it a little so the answers are not there. That's okay. Yes, low density, definitely not high density, not closely packed particles either. Right? Compared to the size of the gas molecule, the distance between them is huge. Lots of space. No increase in volume when temperature is increased. Well, that kind of flies in the face of Charles' law, doesn't it? No decrease in volume when pressure is increased. You know, that thumbs its nose at oil. And we're going to look at oil today in the lab. Do a little experiment. Okay. 2, pressure is what? What is the definition of pressure? Defined as the mass of an object exerts when at rest? I don't think so. Measured in newtons? What's newtons? Yes, newtons of force. That's part of it, but that's not all of it. Right? Pressure is an intensive property. In other words, it doesn't change with size. So this is size. This is part of the size. Defined as the number of moles, well, we can throw that one out. Defined as the force per unit area. There we go. So pressure is force per unit area by definition. Then we have lots of different units that we can apply to the value of pressure. Ampere is definitely not one. We're talking electricity there. Kilojoule, that's pure energy. Newton, well, it's like before. Newton is force. Gram, there's no force there. I mean, not inherently in that unit. Pascal's the only one that fits. In fact, Pascal is the definition of the SI unit for pressure is the Pascal. Let's see. Hey, what is it? It's a Newton per square meter. Technically speaking, both of these are derived units. I mean, this is a fundamental unit, but you square it, that's a derivation. Newton is a derivation. Where's the Newton come from? You remember? Yes. Newton's second law. That's why they call it the Newton, probably. To honor Newton for his second law of motion. Okay. All right, so we can skip 4 and 5. There we go. So a glass column is filled with mercury and inverted in a pool of mercury. Who does that sound like? Torcelli. That we probably wouldn't dunk our hand in the mercury these days. We'd use a device of some kind. The mercury column stabilizes at a height of 729 millimeters above the pool. What's the pressure in atmospheres? Okay, so this is a typical word problem. Lots of unnecessary information. What you need to focus on is that right there, and the fact that it's mercury. 729 millimeters of mercury is our starting point. And we want to end up with atmosphere, right? So how do we get there? Get conversion factor. This is simple dimensional analysis. Is 1 atmosphere. So I'll divide 760 into 729. We can probably estimate that without even doing a without even doing a calculation, right? 760 and 729, it's not going to be more than one. Definitely not 456 atmospheres. So it's going to be less than one. So it could be either this one or this one or this one, right? That's not anywhere near half of this value, so it can't be that. Is it 3/4? No, it's not even 3/4. 3/4 would be in the neighborhood of, let's see, this would have to be 500 something. Need that one. It's got to be this one right here. They're very close to one another. So, right, if your calculator goes on the fritz and I don't have one below you, you can figure that one out. That's the beauty of multiple choice. All right, let's take a look at 6 and see if that's anything new. The local weather forecaster says the current barometric pressure is 30.4 inches. What's that in atmosphere? Similar situation. I just noticed that missing the answer here. I don't know.
It says 1.
It's supposed to be 1.
Yeah.
1 atmosphere. Okay. Somehow or other, and I know what happened. Sometimes when I convert Word documents to PDFs, it loses information. It must have lost that 1 right there. Okay, so in your useful information, you'll have a conversion factor for inches of mercury. If you use it enough, you'll know that it's 29.92. Right. That's almost identical. It has to be, well, this is a little bit smaller than that, so it has to be greater than 1. Right? Not that greater than 1, or not that greater. So if this is a 1, can't be that. So it has to be this one. So the one that makes sense. All right. How about number 8? Can I page it to 8? Yeah. The air pressure in the inner tube of a tire on a racing bike is in the neighborhood of 112 psi. That's true. I used to ride a 10-speed in Atlanta traffic to go to college for my BS. It was a challenge. Actually, dodging cars was only part of the problem. I had to dodge the grates, storm grates, because they were made out of cast iron, and the ribs ran this way, parallel to the road, and they were about that wide, and my tire was about that wide. So I had to dodge them. Otherwise, I'd go right into one of those grates. But the pressure on the tire for my bike was 80 pounds PSI. These racing bikes are much higher pressure. That minimizes friction. When the tire presses against the pavement, the more it deforms, the more rubber meets the road, which means more friction. So they try to minimize friction with these high pressure tires. And then the question is, convert that to atmospheres. So here you just need to know another conversion factor, right? Pounds per square inch. And that's 14.69 inside. So can we estimate that? Let's see. 10 would be too much. 9 would still be too much. 120, 130. 8. 3 and 8. Pretty close. It's pretty close to 8. So this looks like a good candidate right there. I feel like practicing my estimation skills for this. Number 9. Okay, Boyle's law states what? Right? Without even looking at it. What is Boyle's law? Boyle's law says the pressure times the volume of trapped gas is a constant. If what? oh, excuse me, yes, moles, right, the trapped gas, I implied that before. That's constant, and temperature is constant. Right. Remember the four characteristics? We know pressure, volume, mole, and temperature. We can characterize a gas completely in a physical sense. Okay, so which one matches that? Let's see. Equal amounts of gas occupy the same volume at constant temperature and pressure. I think that comes later. From an Italian, right? Avogadro. The volume of a fixed amount of gas inversely proportional to its pressure at constant temperature. I think that fits. A fixed amount of gas means moles is constant, and constant temperature is okay. So we're letting pressure and volume vary, and they vary inversely. Anytime you get the product of two variables equal to a constant, you have an inverse proportion. And in fact, when you graph it, it'll always be a hyperbola. Okay. We just looked at Avogadro. Equal amounts of gas occupy the same volume and constant temperature pressure. Okay. So we don't need to dwell on that one. How about Charles' law? What two variables we have there? Volume, temperature. Okay. Which one came first, historically speaking? I'm sorry? No, I'm of the law. Which one of the laws came first, historically? Boyle. Yeah. And the reason? Technology. They only had technology to study pressure and volume. Right? They were beginning to get a handle on temperature, but they still hadn't quantified it. They could maintain a temperature. They knew how to do that, but they didn't have a reliable measuring system for temperature yet. So Boyle came first. Then once they had temperatures quantified, Fahrenheit, Celsius scales, then they could look at temperature effect on gases. And that's when Charles stepped in. And then it took a leap for Avogadro to figure out that if you've got volume, temperature, and pressure constant, then the number of moles has to be the same for any two gases. What was that all about? Oh, okay. That's a reminder that Chem 101 meets. I think I need to turn that thing off. It's going to do it again. All right. Now that one's talking. Charles' law. Okay. Let's see. We want to look at. Yeah, we want to look at 12. So I need to scroll that one a little bit. Here we go. Here's a picture of a gas that's trapped in a cylinder with a movable piston. So we can vary the volume. And it doesn't look like there are any valves here. So whatever's trapped in there is constant moles. We don't have to worry about changing moles. It means Avogadro's out. At least Avogadro's out as long as there's no chemical reaction here, right? If there's a chemical reaction in there, then you can change the number of moles of gas without a valve. In this case, we've got 10 kilograms sitting on top of that. And how many of the following processes will cause the piston to move away from the base? So the volume will increase and the pressure will decrease for this gas. Now I need to scroll again to pick up our selections. Okay, how many of these? Yeah, how many of those, Roman numeral 1 through 4, will increase volume and decrease pressure? What if we heat it? Well, that'll increase volume, won't it? Let's see, will it decrease pressure? I don't think so. This pressure is constant. Right? We've got this 10 kilograms in the Earth's gravitational field is applying a constant force. Right? So that force, that pressure is constant. It will not change. The volume increases, but the pressure doesn't change. So one can't be it. Remove some of the helium from the container. What happens if you remove the helium? Well, the pressure is temporarily decreased, but will eventually stabilize because you still got that same force pressing on it. You'll decrease the volume, but the pressure won't change again. How about turning the container on its side? That ought to do it. Turn it on its side, then you don't have that 10 kilograms pushing on it, and it will expand its volume. So 3 is a candidate. How about this one? Decrease the pressure outside the container. That ought to do it too, right? Because it's not just the 10 kilograms here. We don't indicate it, but there's air pressure there. So if you decrease the pressure outside the container, yeah, you get a change. So 3 and 4 are good answers. And our selections are 0, 1, 2, 3, 2, 1, 2, 3, 4. So let me scroll. Here we go. See, 2 of those work. Let's see. What do I have checked off next? I always skip 13, 14. How about 15? Well, I should have scrolled a little further. So. There we go. Gaseous chlorine is held in 2 separate containers at identical temperatures and pressures. The volume of the container 1 is 1.3 liters and it contains 6.7 moles of gas. The volume of container 2 is 2.33 liters. How many moles of gas are in container 2? Right. Which law are we using? Well, first of all, we have 2 separate containers at identical temperatures. So the temperatures are constant and the pressures are constant inside these 2 containers. 1 and 2. The volume of this container is 1.3 liters. 1.3 liters. And the volume of this one is 2.33 liters. And moles in the first one is 6.7. And the question is, how many moles in this one? Okay. What are we looking at here? We're looking at a before and after, sort of. We're comparing 2 gases in terms of their moles and volume, which means Avogadro, correct? And one other way you can look at it is PV over NT, initial, equals PV over NT, oops, temperature, that's time, temperature. And all we have to do is find out which ones are constant, right? This is combined gas law. So the ones, temperature is constant, right? Get rid of that one. Pressure is constant, get rid of that. So there we have a relationship of volume to moles. And the volume for the first one is 1.30 liters. Volume for the second one is 2.33 liters. Moles for the first one is 6.70 moles. And that's enough. So all we have to do is divide this one by that and divide that product by that quotient of this one. And we get our answer. And to save me the embarrassment of calculating it wrong, the answer should be 2.51 liters. Excuse me. Hold on a second. Oh. Moles, right?
You were looking at the answers for 60.
Oh, yeah. Okay. So this is liters, and this is moles. Yeah, right, you're right. 12 moles. Let's see, does that make sense? If this one sort of doubles to that one, then this one sort of doubles to that one. Yeah, that makes sense. Around 12. So the moral of that story is, aside from the fact that it's Avogadro's law, we can compare those two gases and use the law to compare two entirely different gases, because ideal gases behave alike. So it's not as if we had one trapped gas and we made those changes to it. We got two separate gases, and if we know the conditions that we're comparing, we can solve for an unknown using Avogadro's law. In fact, we can do that with any of the laws. All right. 18. Let's take a look at 18. And I'm going to have to scroll that one too. Body temperature is about 309 K. Is that true? What is body temperature in Celsius? Remember? No. Everybody knows 98.6.
It's like
Yeah, 37. 37 if you use the convert Fahrenheit to Celsius, you'll end up with exactly 37.
I guess because it's always in the 30s when Europeans are complaining about how hot it is.
Uh-huh. See, 273, isn't it? What's that? So 310, 309, that, I think that's a little low. I think,
The temperature varies by 1 degree throughout the day.
yeah. And when they measure your temperature coming in the door, that's your skin temperature.
I always thought that was like kind of weird that it could just like look at you, because that's kind of its measuring the temperature that your skin is.
Mm-hmm. Yeah.
Like real thermometer stuff, either got like in your mouth.
Right. Right. The most accurate measurement of your body temperatures, the unpleasant side.
It's pretty close to my normal body temperature. My normal body temperature is a little lower than 98.6. It's like 98.2. It gave me 97.9 when I came in.
Right. And medications will affect your temperature too.
That's probably got something to do with it.
Yeah. Yeah. But they're using an infrared thermometer in that talking machine that looks at you. Okay. So body temperatures, we're going to assume it's this. On a cold day, what volume of air at 276 must a person with a lung capacity of 2.2 liters bring into to fill their lungs? So In these gas problems, many of them, you need to decide whether you've got a before-after situation or a state function. If you have a state function, you're using the ideal gas equation because you don't know how you got there. But if you've got a change, you got a before and after situation like this one, 309 before and 276, actually 276 before, draw the air into your lungs at 309 is after. And then with a lung capacity of 2.2, so what temperature is 2.2 liters? It's 309. So whichever one you do, if you say, let's just say V1 T1 and V2 T2. So if we say the volume 1 is 2.2 liters, then it has to be at that temperature, 309 K. Okay. And outside the body is 276 temperature. So this is our unknown. And you just plug it in. Charles' law. It doesn't matter which side, as long as the ones are together and the twos are together. And you plug it in there and solve for this one. So that one, this one, divided by that one. No, this one divided by that one times that one will give you. So it should be less than 2.2. Because if you're going to divide this one by that one, that makes it smaller than 1. And times this one decreases that value. So it should be in this neighborhood. And actually, it could be this one or it could be that one. So you're going to have to do the calculation to find it. Because estimation will get you there with those selections. Let's see, that was 18. Let's see. Yeah, let's look at 20. 20 is an interesting problem. Not so much quantitative, but logical. So you got two balloons, an orange and a blue one. You got orange and a blue balloon. I don't know what the volumes are yet. I'm just saying this one's orange. This one's blue, right? The orange balloon is filled with neon. And the blue balloon is filled with argon. Okay. The orange balloon has twice the volume of the blue. Okay. So that one has twice the volume of this one. So let's shrink this one down. That. So this volume, the volume of a neon balloon is equal to twice this one. Okay. Let's see, which of the following best represents the mass ratio of neon to argon? So we want to know mass of neon ratio to the mass of argon. Well, first of all, what can we glean from this? Does it tell us anything? It just tells us about volume and the gases that are there. So we have to assume that the temperatures are constant and the we know the volumes are different. Moles are going to be different too. Pressure is constant. Temperature and pressure are constant. So we're talking about a relationship of volume and moles. So if you've got twice the moles here than twice the volume here than there, you've got twice the moles. Right? So we can also say that the moles of neon are twice the moles of argon. Okay. Now, to say anything about mass, we have to go to the periodic table. Because this problem in and of itself doesn't give us any information about mass. So argon and neon relationship. I think neon's in the neighborhood of 20. Yeah, neon's in the neighborhood of 20, argon's in the neighborhood of 40. So this would be 20 and 40. Okay. So what's the mole relationship here? Well, neon is twice the number of moles as argon. But argon is twice the mass of neon. So they balance out. Right? Mass ratio is 1 to 1. 1 to 1. It always helps to draw pictures. Let's see, 1820. Oh, that was 20. 29. Let's see if I can page down to 29. Come on. Yep. Just barely caught it at the bottom. Okay, a gas sample is heated from minus 20 to 57, and the volume is increased from 2 liters to 4.5 liters. If the initial pressure is 0.14, what's the final pressure? Okay. First of all, are we going to need a state function, or is this a before and after situation? Yeah, before and after. You got 2 temperatures, you got 2 volumes, and we want to know what the final pressure is compared to an initial pressure. What we don't have is a clear-cut 2-variable law to work with. In fact, we've got 3 variables here. So that means you're going to be working with the combined gas law. Cursor's getting on my nerves. So it's my own fault. I'm leaving it there. Okay, so we've got temperature. Let's write the combined gas law first. All right, initial. Final. Okay, we're going to let temperature vary, so we've got to keep that one. Volume varies, we've got to keep that one. Pressure's going to vary, so we've got to keep that one. Moles is the same. A gas sample is heated. All right, so we can get rid of moles. There we go. So now we have to be sure that we're putting our values in the right place. If you can depend on your ability to walk a tightrope without a net, then you can take those values from the problem and put them right in there. But if you have any doubts about your ability to do that, you ought to set up just a list and put your values in there. Extract them from the problem first. Heated from initial temperature is minus 20. Minus 20. That means the final temperature is 57. Okay. Now, what else are we going to have to do? We're going to have to change those temperatures. Volume increased from 2 to 4.5. So initial volume is 2 to 4.5 final. Okay. And initial pressure is 0.14 atmosphere. That's our unknown. So now that we have everything in its proper place, we can plug it in the formula, confident that we'll get the right answer. Does it matter what these values are? I mean, what these units are? No. It's just that once you change this to Kelvin, and if you use anything in here, we could use cubic meters or, I don't know, gallons, whatever. If one of them is an unknown, the answer is going to come out in the same units as that went in. So if this is atmosphere, that's going to be in atmospheres, which is what we need. Atmospheres. But if we use anything else in there, like PSI, then this answer would come out PSI. It's not picky about pressure and volume, and well, moles is a given. But if we plug those values into this formula and solve for this unknown right here, then we should get 0.0811 atmospheres. Okay. And maybe your mind is really sharp that day. You don't need to do that. But if you like mine, occasionally there's a fog. So you have to be real careful about how you solve a problem. And that's one way to do it. Just, constant, yeah. I can say that. Okay, 30. Can we get 30? I'll read it for you. A sample of oxygen gas has a volume of 1.72 liters at let me scroll back. The whole purpose of putting this thing on the board is so it moves along with our discussion. Okay, so is this a state function or before after? You give one volume, one temperature, and one pressure. And it asks you about molecules. This is a state function. We need the ideal gas equation. Okay. Now, what are our units? Well, let's see. 1.72 liters. Right there. How about pressure? Pressure is 800 torr. So what are we going to do about that? The thing about the ideal gas equation is it's very picky about units. And the units are based upon what are the units of that constant. So if we use this constant, leave room for moles, that constant, 0.08206, is liter atmospheres per mole K. So that says these have to be our units. We're not just ratioing them like a before after anymore. We have to say liters, we're good there. Pressure, 800 torr. Okay. So what's a torr? A torr is a millimeter of mercury. So you can convert that to atmospheres, which is what we need to do, correct? You can convert that to atmospheres by dividing 760. Okay. Moles, that's our unknown. That's what we're solving for. And temperature is, be sure I'm still looking at this one right. 27. 27 plus 273. Now we're good to go. And you just solve for this unknown. Resolve that one times this one, divide by that one, and divide by that one, and you get moles. Now that gives you the moles of oxygen. So then you take the moles, I guess I better do that calculation. This is multi-step problem. So 800 divided by 760 is 1.0526 atmospheres. Now times 1.72, and then divide by 0.08206, and this is in useful information. If you remember it, fine, but if you don't, it's there for you. Did I divide that already? I think I did. We'll soon find out. And then 27 plus 273 and divide that into it also. So I get 7.354 times 10 minus 2. So 7.354 times 10 to the minus 2 moles of oxygen. How many molecules is that? All right, conversion factor for this one. Avogadro's number. So moles needs to be on the bottom to cancel out. 1 mole is 6.022 times 10 to the 23rd molecules. And we get 4 point, let's see. This has all been multiplication division, so I can carry through to the bitter end, and we're limited to 3 significant figures. 4.43 times 10 to the 22nd molecule. There it is right there. Okay. All righty. I'm going to skip down to 37. Lots of the repetition here. Probably already noticed that. If you look through if you try to work any of these, you'll notice that there's a lot of repetition. Which conditions of pressure, temperature, and moles, respectively, are most ideal? Now, in the introduction of this material, I mentioned gases behave ideally under what 2 conditions? Low pressure, high temperature. But I didn't say anything about moles. All right, so here's our opportunity. So here's pressure. So we need low pressure, right? It's either B, D, or E. Right? Process of elimination. How about temperature? High temperature. So that lets this one out. It could be this one or this one. Okay. So how do we select between D and E relative to moles? Which do you think it would be? Gases behave ideally with high moles or low moles? Well, guess what? If you've got low pressure, you're going to have low moles. Everything else being equal. There are certain situations where you can have low pressure with high moles. But low moles is what you're looking for. If you have few molecules in there, then you don't have all that interaction that we're trying to avoid for an ideal gas. Real gases do interact. And the more of them you have in a small space like that, the higher probability they will have to interact. And that just throws your ideal gas out the window. So it needs to be low pressure, high temperature, and low moles. Based upon the kinetic molecular theory, actually. Okay, how about 49? 49. There it is, 49. For which gas are molecules diatomic? For which gas are the molecules diatomic? We only have 1 chapter here. Did we talk about these? This is something that you should have known from the very beginning, actually. Which is okay. I mean, that's fair. Which of these are diatomic? What do we mean by diatomic?
Natural state is 2.
Keep going. Yes, of the same element. So They're bound together covalently. And they're still an element, but they're two atoms together. Remember which ones those were? All the gases? Oxygen, right? Hydrogen, there it is, hydrogen. Nitrogen, oxygen, fluorine, chlorine, bromine. But bromine's a liquid and iodine's a solid, but they're still diatomic. So if we had put either one of these in there, they couldn't be. Why? They may be diatomic, but they're not gases. I was about to say that would be evil of me, wouldn't it? So the diatomic gases here, the only one that's diatomic is chlorine.
That's SAT levels of trickery.
Yeah. Now we have, well, let's let it go. We've answered the question. 52.
What does the last
I'm sorry?
The one before is gas, which gas are the collisions elastic, what is that?
Oh, for which gas are the collisions elastic?
I remember elasticity physics, but
The definition of elastic. Well, an elastic, a 100%, a totally elastic collision is one in which all the energy before, kinetic energy before the collision is equal to the kinetic energy after. There's no loss in kinetic energy before and after. So what's a 100% inelastic collision? That's where you lose all your kinetic energy. In other words, an example, Play-Doh. You make a ball of Play-Doh, drop it on the floor, it goes, it just splats. No more motion, no more kinetic energy. All the energy it gained from falling is dissipated as heat from internal friction. That's inelastic. And elastic, it's difficult to produce a purely elastic collision.
I remember I hated this problem.
But there's what's that ball they used to make? I can't remember the name of it. It's made out of a material that returns almost all of the kinetic energy when you drop it.
Bouncy ball.
Yeah, there's another name. I can't, it escapes me. But you drop it and it'll come up almost to your hand. It's like 99% elastic. We used to play with those all the time. They were really good for making curves and spins. You can spin them when you drop, hit the ground, and it go like that. Because it doesn't lose any energy in the process. Okay, to answer your question, for which gases are collisions elastic? All of them. That's the ideal situation. And that's part of one of the postulates of the kinetic molecular theory. All the collisions are elastic, which means that there's no interaction between the molecules when they hit. The kinetic energy coming in goes out. Now, you may recall that while the kinetic energy may be different, the momentum is conserved. Mass times velocity. Yeah. They couldn't find the name of it. I'll either think of it or look it up myself later. Okay, let's see. The one's what?
The only thing that came up with me was cradle, but I know that's not it. I have one.
Yeah. We didn't look at this one either. For which gas do the molecules have the smallest average kinetic energy? No. Oh, if they're, okay, there must be a condition set up here above. Yes, questions 46 through 51 are part of this. Identical 1 liter flasks contain gases, each at 0 degrees and 1 atmosphere pressure. So they're all at the same pressure, temperature, and volume. Okay, now the questions make sense. So the average velocity, molecules have the highest average. Wait a minute. Hold it. Oh, okay. This is the one I was on, kinetic energy. They all have the same average kinetic energy because temperature is a measure of average kinetic energy. But the other things may vary. Let's see, let's go back up to 48. Which gas has the greatest number of molecules? Right? They all have the same number of molecules. Under those conditions, right, we know that the number of molecules have to be equal. That's what Avogadro said. If all those conditions, pressure, volume, temperature, are identical, then the number of molecules has to be the same. For which gas do the molecules have the highest average velocity? So which one's going to have the highest velocity? One with the smallest molar mass, the smallest molecule. And what law tells us about that one? Graham's law. Where we looked at, let's see, average root mean square velocity is equal to the square root of 3RT divided by molar mass. So the velocity is going to, if this gets bigger, then that gets smaller because this is in the denominator. But if it gets really small, then that one increases for same temperature. So that means helium has to be it. It's the smallest molecule of all these bunch, or the smallest atom, smallest particle, has to be the highest velocity. Which has the highest density? What is density? Look at our definition. Right. Density equals mass per unit volume. Right. So if our volume contains exactly the same number of particles, then we can look at individual ones and assess the mass relationships of these. So if you look at helium, like it's 4 grams per mole. Chlorine is 35, 45, it's like 71 grams per mole. Methane is 12 plus 4 is 16 or 17, right in that range. Right? So it's smaller. Ammonia is 14 plus 3, 17, right? So the heaviest molecule in here is chlorine. So that means its density would be greater also, right? Same number of particles, but each one of those particles is massive compared to the rest. So that's why the density of the chlorine gas should be higher. And in fact, if you have a chlorine spill, chlorine is kind of a yellowish color. You can watch it. Like if you spill it on the table, it'll go right off the table, right to the ground. It's heavier than air. So that's a good thing, actually, because you keep your head up here, then you don't breathe in the chlorine. All right. Oh, wasn't planning on it, but that was good. You did all of it. Let's see. Where am I headed? 56. All right, I need to scroll on that one. 56. Let's see. All right. 56. Which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and temperature? All right. So let's work backwards. Volume is constant. Temperature is constant. 1 gram. Mass is constant. 1 gram each. And what we're varying is with different gases. Different gases. We're looking at different molar masses. Okay, and we want to plot molar mass relative to pressure. Okay, so we want to plot, let's see, pressure versus molar mass. Pressure versus molecular weight. That's our target. All right. So let's see if we can figure out what the relationship is here. If the volume and temperature are the same, and we got the same mass of each one, what's going to vary? The number of moles will vary. We have the volume temperature, and we're allowing the pressure to vary. So the pressure, we're actually plotting pressure versus moles. But this is representative of molecular weight. That's not right. Hold on a second. I'm jumping too far ahead. How do we get molecular weight? Molecular weight is mass per moles, correct? Okay. Mass is constant, 1 gram. Okay. And molecular weight is going to be different. So what does that mean? As we get a higher molecular weight, the number of moles has to decrease. Okay. So if we're going to plot molecular weight against pressure, what's our relationship here? The relationship we know of is PV equals nRT. So we're saying as the number of moles go up, the pressure goes up, right? So if we were plotting, let's just say we were plotting the number of moles. Number of moles versus pressure would be like that. Okay. But what we're actually comparing is molecular weight. So let's combine these. Let's solve this for moles. Moles equals mass per molecular weight. Then if we put this in here, it's crapping out on me. See if I got another one. Purple. Oops. I accidentally pushed these buttons. There we go. So if we plug that value in here, we get pressure, volume equals mass, molecular weight, or molar mass, times RT. Okay? So volume and temperature and mass are all constant. That's constant. Mass is constant, R is constant, T is constant. So let's put all our constants on one side of the equation. and put the variables on the other side. So if we do that, if we pull this one over here, that means pressure times molecular weight equals mass, gas constant, temperature divided by volume. And that's a constant. So what do we have? We have these two variables, pressure and molecular weight equals a constant, which says what? Hyperbola. It's going to look like that, right? Negative slope. I mean, the negative slope changes. Like instantaneous slope would be like this here and be like that there and like that there, but it's still negative. So do we have any of those that look like that? The closest one we have is this one, but it's still not right because the relationship is not a straight line. It's a hyperbola. So the answer to this one is E, and that's wrong. That's wrong. E is the answer, not C, and not D. Okay. Did I lose anybody in that discussion? Okay. All right, so I need to make that correction. Maybe I don't. Yeah. I make it the correct, it's correct here, but it's not right there. Okay. Let me make myself a note. Let's see. Check Blackboard version. Did anybody try to work this one and find that answer? Didn't get that far? Okay. 56, 61. See if I can page down to 61. Yep. Okay. Let's just read the question. When 0.72 grams of a liquid is vaporized at 110 degrees at 0.967 atmospheres, the gas occupies a volume of 0.559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Aha. Okay, read backwards. What's the molecular formula? What do we need to know to find the molecular formula? We need to know that multiplier. Remember? Okay, how do we find that multiplier? Ratio the true molar mass of the compound with its empirical mass. So the empirical mass here is what? The empirical weight is 12.01 plus 2.02, which is equal to 14.03 grams per mole. Okay. So what we need to know is the molar mass. Can we find it from this information? Well, let's see. Do we have the mass? Yep, we got the mass of it right here. So we have the mass, molecular weight equals mass per mole. We have the mass at 0.72 grams. We need the moles. Can we get the moles from this? Let's see. We got temperature, we got pressure, we got volume. Yeah. The ideal gas equation will give us moles. Solve for moles. Okay. So pressure is what? 0. Let's see, I didn't give myself much room. Let me go back this way. So the pressure is 0.967 atmospheres. I'm gonna leave the units out. And volume is what? In liters. 0.559 liters. Okay, I did write that one in. R, 0.08206 liter atmospheres per mole K. And then the temperature, 110 C. which is, I'll do that in my head. 383, right? Three, 83. Yep. 383K. All right, so that gives us the number of moles. Plug it in here, we find the molar mass. So let's do that. 0.967, 0.559, 0.08206 divided into that, and 383 divided into that. So I get 1.72 times 10 to the minus 2. (1.72) times 10 to the minus 2. So let's divide that into 0.72. I get 41.9. 41.9 grams per mole. All right. So 41.9 divided by 14.03 equals what? That's the ratio we need to find that multiplier. The nearest one I get is 3. So we should have equals 3. That means this is going to be C3H6, correct? Okay, there it is. C is your answer. So what's the trick to this one? Working backwards. What do you need? You need to know that value right there. So then you think, how do we get that value? You ratio the two, molar mass to empirical mass. So do you have the molar mass? No, not yet. Do I have the information I need to get it? Well, we do have this based on that definition. And then what else do we need? What is this problem anyway? It's the Dumas method. Yeah, the Dumas method. And we're going to do that. I think that's the last lab in the list. 61. Let's see. How are we doing on time? 20. Let's see. I skipped all the way down to 80. One more. There it is. We've already done this type of problem, where you combine equations, you substitute values. Actually, not values. You substitute equivalent expressions from one equation into another. It's kind of like solving simultaneous equations in algebra. You all remember how to do that. This is similar concept. If M equals molar mass, R is the gas constant, T is the temperature, P is the pressure, which of the following expressions represents the density of a gas? Okay, what's the definition of density? Density is mass per unit volume. Okay. What else do we have? We got the gas constant, we got temperature, we got pressure, and we got molar mass. What are we working with here? We got their R's, we got our molar masses, we got pressures and temperatures. Okay. So that looks to me like we're going to need access to this one. Right? And then we need an expression for molar mass. Mass per mole. Okay, so we got to reduce this one to these common terms where we're equal to, let's see, which of the following represents the density of the gas? So we need the density equal to something. So that means we're coming back to this one. So, let's see, let's look at what we got here. There's no mass in there. So we got to substitute something in for mass. That doesn't include mass. Right? And there's no volume there. So we got to substitute in something for volume. Got to get rid of the volume and the mass. Right? So if we want to substitute in mass, then solve this one for M equals molar mass times moles. And if we're going to substitute volume, solve this one for volume. Okay, now we can substitute in here like this. So that one is molar mass times moles in the numerator, and the volume is nRT divided by P. Okay. Well, let's see. Remember, the denominator of the denominator is the numerator, which means you take this expression and just flip it like that. Now we've got M times N times P divided by nRT. Moles cancel, and we've got molar mass times pressure over RT. Molar mass times pressure divided by RT. That's it. Okay. All right, that was 80. 81. We're going to check the time. How much time do we have? I don't want to eat up your lab time. That lab is too fun to do. We got an hour left.
10:30.
Okay, we're good. Let's see, just did 80. 81. I got to scroll. There we go. One way to isolate metals from their ores is to react the metal oxide with carbon, as shown in this reaction. So this is, I assume this is some metal. We don't know what it is. Reacted with carbon and gives you the pure metal plus carbon dioxide. Right? So what are we doing here? Right? Carbon's going from, remember, oxidation states. We did talk about that, haven't we? Oxidation states, carbon 0. Carbon here is +4, right? So it's given up 4 electrons. Those 4 electrons went in here and made this one 0. That's actually what's happening in this reaction. It's an oxidation reduction. Okay, if 34.08 grams of metal oxide reacted with excess carbon, right, so we don't have a limiting reactant there, and 4.37 liters of carbon dioxide formed at 100 degrees and Celsius and 1.5 atmospheres, what's the identity of the metal? What do we need to know to identify that metal? One of 2 things. Either the atomic number, right, number of protons. Can we get the protons from this? I don't think so. So our next best thing is molar mass, because molar masses of the elements do change also as you go from top to bottom, left to right. They increase. And most of them are far enough apart from each other that you can discern what element is which based on their molar masses. So let's see, if we're going to do molar mass, let's see, since M is already taken, I'll say MW, and that's mass per number of moles. What do we have here? Well, the metal oxide, yeah. but we don't have the mass of the metal. We have the grams of the metal oxide. And since we don't know what the metal is, we can't calculate moles from that. Right, we got to get at moles. The only way to move around in this equation is the same as it's always been. You got to know moles. So can we find moles? Well, we know the volume of carbon dioxide. We know the temperature. We know the pressure. Yeah, we can find moles. PV equals nRT, and moles is equal to PV over RT. So the pressure is 1.5 atmospheres. Volume is 4.37 liters. R is same as it's always been. Why they call it a constant. And the temperature, 100 plus 273. That should be easy. Okay. Now we'll find out how many moles of carbon dioxide were produced. So let's see, 1.5 times 4.37 divided by 0.08206 and divided by 3. So we have 0.214. 0.214 moles. And that's carbon dioxide. Okay, so how many moles of the metal do we have? Well, we have twice that many, don't we? Right, the ratio is 1 to 2. So we actually have moles of metal is 0.428 moles of N. Okay, does that get us anywhere? Okay. I have a solution. You're gonna love this. If we know the moles of carbon dioxide, we can determine the mass, correct? The mass of carbon dioxide. So 0.214 moles of carbon dioxide. Okay, converted to mass. So we need the molar mass of carbon dioxide, which is what? Let's see. 12.01 plus 32. What is that? 40. 4401. Yeah, 4401. 44.01 times 0.214. And I get 9.43 grams. 9.43 grams of CO2. Okay. Okay, so we know how the mass of this. What we're trying to get at is the mass of that one because we got the moles already. We need mass. So if we know the total mass, then we subtract that from the total and find out what this is. Okay. So how about the mass of carbon? Right? We know the mass of this metal oxide. How about the mass of the carbon? How much mass of carbon did it take? Well, we know that the moles of this metal oxide are equal to the moles of the metal. So it's 0.428 moles of this. And this is equal to the moles of carbon dioxide because they're 1 to 1. So it's 0.214 moles of carbon. 0.214 moles of carbon is what's mass? 12.01. And 0.214 4 is 2.57. 2.57 grams of carbon. So the total mass is 3408. Thirty-six point 65. That's total. Right? And what did Lavoisier say? Conservation of mass. So we got to have the same mass over here as we started with. So if we 36.65 is the total, and we know that this is 9.43 here, then what's left over is that. So we subtract 9.43 from this one, which would be 27.22 grams is our metal. So 27.22 grams for how many moles? 0.428 moles of metal. And that's equal to what? 27.22.428 divided is 63.6 grams per mole. 63.6 grams per mole. Now you have to go to the periodic table. 63.6. That's not getting close. Looks like copper is the closest one. There. Okay. We had to dance around the barn quite a bit to get that. But as long as you have a clear vision of what you need, then you can find out. At least on my test, you can. The information is there somewhere, either here or in the periodic table or in the useful information. So we all worked upon this premise. Molecular weight equals that and that. Say, okay, we can find this one, right? Stoichiometry tells us this one. Stoichiometry also tells us this one, but we had to do these calculations to get there. All right, that was 81. Let's see, 82. After that, this one's going to be simple. I just have to get back on track here. 82. There. The standard temperature for gases is what? Did I tell you this one? What's the standard temperature for gas? You know, STP, standard temperature and pressure. Standard pressure of gas is 1 atmosphere. That's the same for all chemistry. But the standard temperature for gas is different than the standard temperature for all other chemical processes. Standard temperature for gas is 0 degrees Celsius, right? Which is 273 K. Everything else in chemistry is 25 degrees Celsius. So that's why this is the answer. Standard pressure for gases, I already told you that one. So 1 atmosphere. I think that's the reason I put these in here, just so I'd be sure and get that information across. 82, 83, 86. Okay, 142 milliliter sample of gas is collected over water at this temperature and at that pressure, 753.4. What's the volume of the dry gas at standard temperature and pressure? Okay, what are we looking at here? If we collect the gas over water, how do we do it? Well, we had a container of water, right? And we had probably an inverted graduated cylinder. See this is a solid base. So it's marked off here with volume. And it's filled with water completely. Just like with Torricelli did with his barometer, you fill this thing up, you plug it, and invert it in there. And it's going to mostly stay up there. Even if it does drop, what's going to be up in here? The vacuum, right? But, not a vacuum. Why? Because water is volatile to a certain extent. At 22 degrees, it will produce 20 torr pressure into a vacuum. Plus, our gas is going to come in here like this, that, and bubble up here, and collect at the top. Okay, so what's in that space? There's our gas plus water vapor. Okay, so when they say dry gas at standard temperature pressure, we've got to subtract the pressure due to water. Okay, so what's the volume of the dry gas? Well, the first thing you have to do is say, do we know what the pressure of the combination is? Yes, 753 torr. So the pressure of the dry gas is minus the water vapor. So now that you have the pressure, the temperature, and the volume, and, well, actually, that's not your temperature, is it? No, that's not your temperature. Your temperature is here because the question is standard temperature and pressure. So now we have a before and after situation. Right? This is the pressure before. So pressure initial is 733 torr. Pressure final is question. No, excuse me, volume. Excuse me, volume. The pressure final is 1 atmosphere, 760 torr. The volume doesn't change, right? Because it only says standard temperature and pressure. So the volume is constant at 142 milliliters. But how about the temperature? Well, the temperature for this is 22 degrees. So the temperature initial is 22 plus 273. The temperature final is equal to 273, standard temperature. So now we have a before and after, right? PV over NT, PV over NT. This is initial, this is final. So the number of moles doesn't change. It's the same gas before and after. Temperature changes. We have to keep that. Pressure changes. Right, between those two. Volume initial, let's see, volume doesn't change either, right? What's the question again? What is the volume? Oh, so we need to keep the volume, excuse me. Okay, so we've got temperature changing, volume changing, and we know the initial volume, but we don't know the final volume. So that is the unknown right there. Let's see if my logic works. I'm just curious. So if we solve for the final volume, we need to know initial pressure, initial volume, times final temperature over initial temperature divided by final pressure. Okay. So initial pressure, and do we need to change those values? Not for before and after. That's just the temperature that needs to be changed. So this temperature is 295. Okay. So now we're going to plug in initial pressure is 733. Initial volume is 142 milliliters. Initial temperature, final temperature, excuse me, is standard 273. Initial temperature is 295. And final pressure is 1 atmosphere, 760. There we go. So that should give us the correct answer. 273. Okay, divide by 295 and divide by 760. So I get 127 milliliters. None of these. Close, no cigar. Oops. That was 86. Yeah, 86. What was the other one? All right. 86, let's go down to 94. And let me scroll. So we'll get all the answers in there too. Did we do one of these in class? You have two bulbs connected by a valve. And this one's 3 liters and that one's 2 liters. And this one contains a gas under pressure. This one contains the gas under pressure at 1.8 atmospheres. This one, 3 liter, contains a gas under pressure at 3 atmospheres. Okay. When we open the valve, we want to determine the final pressure. And the temperature remains constant. Okay. Did we do one of these in class? Okay. We'll do one now. All right. So that's not going to show up very well. So at first glance, this looks like an unsolvable problem. Until you realize that regardless of what gases are contained in here, doesn't matter what the gas is, you can treat them as gas A and gas B. And based on Dalton's law of partial pressure, we want to know the final pressure, the total pressure. Then we just need to know the pressure of the 3 liter plus the pressure of the 2 liter. So let's see, qualitatively speaking, when we open that valve, which way is the gas going to go? Yeah, it's going to go from here to here because that's higher pressure. So the pressure, the final pressure should be somewhere between 3 and 1.8. Right? This one's going to decrease and that one's going to increase and they meet in the middle somewhere. Okay, so that's kind of a qualitative estimation so that we know if we get a value here greater than 3 or less than 1.8, we know we did something wrong. Okay, Dalton's law says all we need to know is the partial pressure of this one and then the partial pressure of that one and add them together. So if we treat them separately, let's say for argument's sake, that's a vacuum. So we open this valve and that gas rushes into the vacuum until it's equalized. Okay, do the same thing for this one. Treat that one as a vacuum. Then this one produces a partial pressure in both of the bulbs. Then we add those two together and we get the final pressure. Now, how do I know that this works? Because this experiment has been done in the lab. And the measurement's been made and confirmed that, yeah, it works. So to do this one, the initial volume here is 3 liters, right? What's the final volume? That's the total, correct? 5 liters. Okay. Initial pressure is 3 atmospheres. Final pressure is what we're looking for. Okay. So, what's the relationship? PV equals PV. PI, VI equals PF, VF. Boyle's law. So if we say PI, VI equals PF, VF, we're solving for PF here. So we need to be PI over VI divided by PF. Will give us the final volume. Okay, so now we have the initial pressure is 3. The initial volume is 3. And the final volume is 5. So that's what, 9/5? 9/5 for the pressure contributed by this one. 9/5 atmospheres. Okay. Now, this one, the initial, I'll just do it over here. The final volume is the same. The initial volume is 2. And the initial pressure is 1.8. Okay. So now we put in initial pressure, 1.8 atmospheres. The initial volume is 2. And the final volume is the same as before. Okay. So what's that? 3.6. Okay, so this is 3.6 divided by 5 plus 3.6 divided by 5. So what's the total? 12.6. 12.6 divided by 5. Right? Do we need to calculate that out? What's 5 into 12.6? It's about, let's see, 2.5, roughly. So the closest one to that one is this one right here. So if we do that calculation, it should be 2.52. So there we use both Boyle's and Dalton to solve this problem. That was 94, 95. Right. Let's scroll again. Here we go. The partial pressures of methane, nitrogen gas, and oxygen gas in the sample of gas were found to be 1.35. Oh, I chopped that one off. What is it supposed to be? 508. 135, 508, and 571, respectively. Calculate the mole fraction of nitrogen. What do we know about the relationship of pressure and moles? They're directly proportional. So all other things being equal, as the pressure increases, the moles increase. So if we ratio the pressure, we're also ratioing the moles. So what is it? Mole fraction of nitrogen. So we need nitrogen, which is 508, correct? 508 divided by the total. 135 plus 508 plus 571. That should be the mole fraction of nitrogen, which is let's see, five, that's 1,080, 1,100, 1,200, and 15 or 16. 508. So that should be over 2. Correct? Oh, no, it's a fraction. 0.5. The neighborhood of 0.5. Okay, we're going to have to calculate that. I can't estimate and choose. Total those up and then divide 508. 0.42. 0.418. Yeah. 0.418 is the mole fraction of nitrogen. Okay. Notice that when you do that, if you do it this way, that has to be in both of them. Because you need the total in the denominator. Let's see. 96. Dalton's law of partial pressure states, well, we just used it. We all know what it means. The total pressure of a mixture of gases is the sum of the partial pressures of all the gaseous compounds in that mixture. Let's see, 103. CIR. I don't listen to them. Just hear it advertised all the time. Come on. There we go. 103. Calculate the root mean square velocity for oxygen molecules in a sample of oxygen gas at 11.8 degrees Celsius. Okay, I put that formula up there earlier, didn't I? The root mean square velocity equals the square root of 3RT divided by the molar mass. So we need to know the molar mass of oxygen, which is 32. Wait a minute. Joules per K mole. What's unique about that? Use a standard units of mass, which is kilograms. So we need this in kilograms. If that's grams per mole, then grams per mole and kilograms per mole, we have taken 1,000 parts of that and put it in this prefix, which means this value has to be times 10 to the minus 3. So times 10 to the minus 3, 32 times 10 to the minus 3 kilograms per mole. Okay? Does that make sense? If it's 32 grams per mole, should it be larger or smaller if you change the unit to kilograms? Kilograms, if the size of the unit increases, then the number has to decrease. So yeah, we went to the negative. Just checking myself. Okay, we got that value. We got this value. We got R, 83145. 8.3145. T equals 11.8 plus 273. And if you multiply these three together, divide by that, take square root, you should get 471 meters per second. Okay. So that was really a simple calculation. And the test there is to remember what to do with the molar mass. You have to change the units. Let's see, did I put a... No, I didn't. If we had used 32 instead of that smaller number, a smaller number in the denominator makes a bigger number, I should have put 0.472, 0.471 meters per second as an answer. Just to test to see if you remembered to do it, because if you didn't, you would get a number a third that size. I mean, 3 orders of magnitude smaller. Okay. 109. We ought to be getting close to the stopping point here in a minute. Which of the following is included as a postulate in the kinetic molecular theory of ideal gas? All right. The distance between gas molecules is small compared to the size. It's just the other way around. The distance is huge compared to the size of the molecule. All collisions between molecules are elastic. Oh yeah, we covered that one earlier. Let's see, do we have any other oddballs in here? Nope. So that has to be it. And the rest of these are going to be false. 111. There we go. Graham's law states. What does Graham's law state? Equal amounts of gas occupy the same volume. These are the same selections as the earlier laws, right? So we already identified that one as Avogadro's. The volume of a fixed amount of gas is inversely proportional to its pressure at constant temperature. That's Boyle's. The volume of a fixed amount of gas is directly proportional to its temperature in Kelvin that must be at constant pressure. The volume of a fixed amount of gas is directly proportional to its temperature. No, that's not Graham's law. That's Charles' law, volume and temperature. The total pressure of a mixture of gases is the simple sum of the partial pressures. That's Dalton's law. Let's see. The rates of effusion of gases are inversely proportional to the square roots of their molar mass. That's Graham's law. I was looking at this and said, that looks a little like a C. It can't be. So it must be an E. All right, 111, 116. Okay, a half hour. 1, 2, 3, 4, 5, 6. I got 6 chosen. Let me see if we can get through these pretty quick. 17. Okay. Order the following increasing rate of effusion. All right, so based upon Graham's law, the rate of effusion should be slower for the larger, the heavier atoms. So if we put them in order, we need to know the molar masses. Right? So fluorine is what? Fluorine is about 19, so that'd be 38. Right, chlorine is 3545 times 2 would be about 70. NO is 14 plus 32, 44? 46, excuse me. Yeah, thank you. And this one adds another oxygen to that one. Right, so that's 62, right? And this one is 12 plus 4 is 16. Okay. So in order, increasing order rate of effusion. Increasing rate of effusion means that the fastest one is going to be the lightest. So it's going to be increasing. Look at all these are to the right. So the fastest one is going to be on this end. So it's either this one or that one. Right? That's the fastest one. How about the slowest one? It's going to be chlorine, correct? So there's chlorine. Okay, we got it. Okay. Hey. We didn't even have to do the rest of it because this is multiple choice. But if we put them in order, they would be like that. 16, and the next one is NO. Did I do this calculation right? No, I didn't. 30. There we go. Then this one, that one, from right to left. That one, that one, that one, That one. Okay, that was 117, 118. Okay, it's on the board. Complete the following. Because real gas particles have attraction for one another, real gases act most ideally at standard temperature and pressure. Well, technically, not most ideally, but they do act ideally at standard temperature and pressure. So let's hold that one in reserve. We assume gas particles have negligible volume. That's true also. Negligible volume. 1 mole of an ideal gas at standard temperature and pressure is 22.4 liters. Because real gas particles have attraction for one another, has nothing to do with this. It has attraction for one another. It has nothing to do with that either. Real gases act more ideally at higher temperatures and lower pressures. That's the one right there. Yeah. And the key, the one that eliminates this one is most ideally. They're not most ideally at standard temperature and pressure. Because what happens if the pressure goes up or down or above or below that value? Then what happens? Well, it's supposed to be most ideally in the middle. It's not. It's when the pressure goes low and the temperature goes high. Right? So A has to be false. Can't be. Right? D is the only one that fits. Mm, 124. Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? Okay. So this one, I don't know if we've discussed this one very much. What you're looking for intermolecular attractions is primarily polarity. Are the molecules polar? The lowest van der Waals correction for intermolecular attractions. The lowest van der Waals corrections would be for the gas that is most ideal. So do we have any inerts in here? No, there are no inerts in there. So now we have to look for first polarity and then size. So ammonia can't work because the ammonia molecule is like this, with electrons up there. It's very polar. The other way you can look at it is, what's the boiling point? If you can assess the boiling points. And we don't do that in this class. We get into that first couple of chapters of second semester. So this wouldn't be a fair question as a required, might be a bonus. So what we need is a small molecule that is not polar. And the smallest molecule in here is hydrogen. And it's also the one of this group with the lowest boiling point. Right? Liquid hydrogen is extremely cold. I think it's a toss-up between liquid hydrogen and liquid helium as to which one's the coldest. I'm trying to think which one is, they're in the neighborhood of 4K. It's their boiling point. I know liquid helium, if you put it in an open container, it's weird. It crawls the walls and comes out. It has something to do with intermolecular and intramolecular attractions. Anyway, that was 124, and the answer is A. 132. There we go. A manometer is attached to a sample of gas. So what's a manometer? It's a modification of a barometer to measure the pressure of a trapped gas. That's a manometer. It's attached to a sample of gas occupying a volume of 2.34 liters. The mercury level in the arm of the manometer attached to the gas sample is 24.3 torr, lower than that of the open arm of it, open to the atmosphere. And an atmospheric pressure is 1.23 atmospheres. What's the pressure of the sample of gas? Okay, this one needs a picture. So we've got a trapped gas here. And it's attached to a manometer that looks like Dalton Boyle's J-tube. Here we go like this. And in this manometer, it's attached to this tube that in this case, the manometer is open to the atmosphere. It's not a vacuum in here. So atmospheric pressure is 1.23 atmospheres. That's pretty high, actually. What are they doing this experiment down by the Dead Sea? Maybe so. This is an Israeli experiment. 1.23 atmospheres from here. Now we've got mercury in there, and the gas sample is 24.3 torr lower than that of this arm. So we've got mercury level here and mercury level here. And the difference between those two is 24.3 torr. Okay? What's the pressure of the sample of the gas? Well, what's the sample of the gas pushing against? Right, it's pushing against this one and that one. So our answers are in torr. So we have to convert this to torr. Right. 1.23 times 760. Is 935 torr. Okay. And then it's also pushing against this much mercury pressure. So we need to add 24.3, 959.3, or this was the best answer. Okay. So that one needed a picture. Let's see. One more. 142. Oops, too far. There we go. Okay, consider the reaction between ethane, C2H6, and oxygen gas to produce carbon dioxide and water. What volume of carbon dioxide will be produced at standard temperature and pressure from the reaction of 4 liters of ethane and 7 liters of oxygen? All right, so we need a balanced equation, I'm pretty sure. This is a stoichiometry problem. So ethane, C2H6 plus oxygen yields what? Carbon dioxide and water. All right. So let's see. I don't think there's any easy way to do this. I'm going to go to the budget. So we got carbon, hydrogen, oxygen. On this side, we've got 2 carbons, 6 hydrogens, 2 oxygens. On this side, we have 1 carbon, 2 hydrogens, and 3 oxygens. Okay. So let's balance the carbons first. Simply because I don't see any reason to start anywhere else. So that's 2 here. That yields 5 oxygens, correct? Now, let's see. Let's balance the hydrogens, 6 hydrogens. So 3 of those make 6 hydrogens plus 3, 4, 7 oxygens. So how do we get 7 oxygens out of this one? Remember the trick? Fraction. 7 halves. And then if we get rid of the fraction, multiply the whole thing through by 2. So there's 2 here, 7 there, 4 here, and 6 here. There's your balanced equation. Okay. Now, what volume of carbon dioxide would be produced at standard temperature and pressure from a reaction of 4 liters of ethane and 7 liters of oxygen? And we want to know the volume here. Okay. When you're given absolute amounts of reactants, both or all, it only takes a couple. You have to assume that one of them is going to run out. So you got to find out which one runs out first, right? What else do we know about this? We know that the number of moles is proportional to the volume. So we don't have to convert to moles. This is our representation of moles here. So if we're all at the same standard temperature and volume here in this space, then what's the relationship? How many liters of this would be produced? Well, 4 liters of this, let's see, 4 liters of C2H6, we can use our coefficients. So 2 for that one and 4 for this one, which means 8 liters of carbon dioxide if we use all this up. Oxygen would be 7 liters. And we do the conversion there. Okay. So this is 7 coefficient for oxygen and 4 for CO2, which means 4 liters of CO2. There it is. We're actually going to produce 4 liters of CO2, and we'll have excess ethane. Okay. Looked like it was going to take a lot more work than it did. Luckily, I didn't try to overthink it. Work through it methodically. The trick to this one is to recognize that the proportionality here is volume and moles go up and down. They can be used interchangeably. Okay, I think that's the last one. Yep. We can take a break and come back.